Hi everyone, and welcome to today's lesson on energy and fields. We're going to start with a quick refresher of fields and potential energy. Then we will move into the meat of today's lesson, the relationship between an object's position in a field and its potential energy. Let's start with a recap of fields. Remember, there are three types of fields: gravitational, electric, and magnetic, all shown here. Fields describe how an object influences other objects in their vicinity and imparts forces on them. The object in each of these three fields that impacts forces on other objects varies depending on the field. For the gravitational field, the object is any body that has mass. We typically talk about gravitational fields in relationship to the planet Earth because of how massive it is and the gravity it creates. It's also very easy and intuitive for us to understand. For the electric field, the object is an electric charge, and similarly for the magnetic field, the object is a magnet. As you can see here, the electric and magnetic fields are very similar, and because of this, they are often referenced together as an electromagnetic field. For the gravitational field, the direction of the field points in the direction of the force that a mass placed in that field would feel. For this example of Earth, we all know by experience that objects experience a force downward. That's why everything falls to Earth and we stay on the ground. The electric field points in the direction of the force on a positive charge, so it points towards a negative charge. And we'll get to this later, but think about magnets and how same-pole magnets repel each other and opposite poles attract. Opposites attract, that's the key here. And the magnetic field points in the direction of the force on the north pole of the magnet. Okay, let's recap potential energy. Potential energy is defined as the ability to do work. The total work done by forces on the body in a field depends only on initial and final positions of the body in the field. It is independent of path, and we will see later this relationship of initial and final positions in work and energy. Okay, let's take an example of a bow and arrow to discuss potential energy. The lady on the left has not drawn back her bow yet, so we know by experience that the arrow will not go very far. It will just fall to the ground in a small parabola. The lady on the right, though, has her bow extended, and we also know by experience that the arrow will go much farther in this case. This is because the drawn bow has more potential energy than the relaxed bow. Another example we're probably all familiar with is dropping a phone. If you drop your phone from a relatively low height, it will have a lower impact and thus less risk of shattering. If you drop it from a higher position, say a bunk bed, its impact on the floor will be higher because raising its height increases its potential energy and the risk increases of it shattering. So that brings us to the main point of this lesson, the relationship between potential energy of an object in a field and its position in the field. As we just saw with the bow and arrow example, the more you extend the bow from its resting position, in other words, the greater the distance from the resting position, the more potential energy it will have. Similarly, for the phone example, the higher off the floor you drop the phone, the more potential energy it will have, and the more likely you're going to have to replace it. So if you increase the distance from your reference position, you increase potential energy. And vice versa, you decrease the distance from your reference position and you decrease the potential energy. Let's look at another example, lifting a box to a table. The boxes shown here have the same dimensions and weight, but we know by experience that lifting the box to the higher table requires more energy on your part or more work. That's because it will have a higher potential energy on the higher table than the lower table. Let's talk briefly about electric and magnetic fields. Imagine you have two magnets of the same pole. What happens when you bring them together? They want to repel each other, right? The same thing happens when you bring two negative electrons together or two positive electrons together. They repel each other. If you bring two magnets together of the same pole, the closer they are together, the more potential energy they have. And if they are very far apart, they have low potential energy. There's not as big of a repelling force there. The opposite goes for a North Pole and a South Pole magnet. The farther away they are, the more potential energy they have because they want to come together. And the closer they are, the less potential energy they have because they're already together. All of this applies to electrons as well. This is because opposites attract and same signs and same poles repel. In terms of why this happens in the field and why the gravitational forces happen in the field as well, let's summarize it with a concise drawing. For gravitational fields, we all instinctively know that the force field points downward to Earth. Again, that's why everything falls and we stay on the ground. Moving an object away from Earth increases its energy because it's moving in the opposite direction of the force field. For electric and magnetic fields, the force field from a positive to a negative charge points in the direction of the negative charge because the electric field is defined as the direction in which a positive charge would move if placed there. Again, opposites attract. Moving the positive charge away from the negative charge and in the opposite direction of the force field increases its potential energy, just like the gravitational field. So there you have it, increasing distance from any reference point in the direction opposite of the force field increases its potential energy and vice versa.